Hello everybody. This week we're going to be talking about relays, breakers, and reclosers. So I'm sure you guys have all seen something that looks like this in the electrical panel at your house. This is a residential grade circuit breaker, and they use something very similar in commercial environments. And while you don't really give them much thought, they work really well. If everything's working fine, you ignore them for years, and if for some reason they trip, you go downstairs, you turn them off, you see that they've indicated orange, you turn them off, you turn them back on again, and away we go. But that breaker is actually doing two separate things for us. Um, and so the first of those is it functions as a switch. You throw the lever and it turns the circuit on or off. And the second thing that it does for us is it acts as a decision maker. It's constantly evaluating the question, is the current that is flowing okay? And if it decides that the amount of current that is flowing is not okay, it will open that circuit up and raise a flag indicating that it saw a fault condition and decided to open or trip. Now, in a molded circuit breaker like these, both of those functions are happening at the same voltage, and they're both happening in the same housing. When we get to the distribution system, things are a little bit different. When we talk about a breaker from the perspective of the distribution system, in common parlance, when we say, oh, the breaker at the station opened, what we're actually talking about is a combination of a breaker, using proper terminology, a breaker, and a relay. So whereas the molded unit has both of those, the decision making and the switch in the same housing, we separate those things at the distribution scale. So the breaker, which is located here, is just the switch. It doesn't have any decision making capability. It accepts an electrical signal to open and close, and that's it. Other than that, these breakers are very heavily built. They're very heavy construction. They're designed to be able to break a very large number of fault amps, often on the order of 40,000 or more. Um, big heavy switches designed to deal with big serious arcs and many, many cycles. The relay in this diagram here, so here's the breaker, there's the relay right there. A relay in modern terms is a specialized computer, and it's designed to monitor line conditions and to signal that breaker whether it should open or close. So once upon a time, relays were actually like discrete parts before electricity existed long before computers did, and breakers and station protections have functioned very much the same since long before computers were around. And so once upon a time there was electromechanical relaying, which used, actual discrete relays and discrete capacitors and springs and electromagnets and all kinds of engineering trickery to achieve what we can very easily do with a computer today. So back in the days when it was all discrete parts, you'd have a station electrician come in and he'd wire things up in the way you wanted, and that's how you defined your behavior, by how it was wired. And they defined different wiring blocks that would do different things for them. And they developed a standard set of nomenclature. The IEEE is back here, standards. And they gave all of these different wiring blocks and functions numbers. So, here's sort of a table showing some of the common numbers. A 51P would be an inverse time overcurrent protection. So if you want to have your relay make decisions using a curve that looks something like a fuse curve, you'd be looking at a 51P relay. If you were looking at a ground protection, so now you're looking at the imbalance current between three phases, you'd be looking for a 51G element. Um, you know, you can do 51p if you want an instantaneous protection as well. So, you know, if you ever hit this current trip, I don't care for how long, that would be your instantaneous overcurrent protection. Modern relaying can do negative sequence where you do a lot of fancy math and you're able to determine if you've got a high impedance fault somewhere way down line. And the other important one to us today is our 79 element, which is a reclosing function. And what this would do is this would allow the breaker to trip, delay, and then try again. And this is really, really useful to us when we get to dealing with things that would be otherwise considered a temporary fault. So before we get into temporary faults, commonly when we're just talking and we talk about the breaker, we're actually talking about the combination of a breaker and a relay working together. Now, when we talk about a recloser in common terms, we're not talking about just a 79 element inside a wiring cabinet. What we're talking about is a standalone switch combined with a relay. So, a couple differences, and you might say, wow, it sounds a lot like a breaker, and you'd be absolutely right. It is a lot like a breaker. The differences between a breaker and a recloser is in their fault break ratings. So, fault break ratings on a breaker, very, very high. They're going to be a lot lower on a recloser. So this could be on the order of 40,000 amps, whereas this would be on the order of 13,000 amps, right? So much, much less in terms of fault breaking capability. But what you lose in fault breaking capability, you gain in compactness and lightweight. So breakers were designed to be installed at the station. Reclosers were designed to be installed in the field. If we think about the station, we're riding close. We don't have any line impedance. We saw when we were doing our fault current evaluations that the less line you had between you and the state and the source, the higher the fault current was, which is why those breakers have to be so robust. Whereas the reclosers, which were designed to be installed way down the line, have the benefit of that line impedance, slowing, damping that available fault current down. So we saw a breaker. Here's an example of a vacuum bottle style recloser. So let's take a look at the elements that we've got here. We've got a high voltage line tap. We've got these three symmetrical units. They're all the same. And each one of these has a vacuum bottle style switch. We'll be talking about those next lecture. So we come in, the bushing's covered up with some animal guards, always good practice. We come in, we've got a high side arrestor, and we've got actually on these there is no really high and low side, and reclosers were designed explicitly with the idea of reverse power flow in mind. So you could put one of these at a tie point between two feeders, for example, and so it might be feeding from the left or it might be feeding from the right. It really doesn't matter. So they call this X and Y bushings. Right, so you've got an arrestor on the X bushing side, you've got an arrestor on the Y bushing side. Over here, we've got PTs. So here we go from our primary side voltage, and this will step that down to 120 volts and send that down to the control cabinet, which will be located somewhere near the base of the pole. Right, usually right about 6 feet high, you'll have a control cabinet mounted on the post. And so those PTs are going to send their signals down there, and the relay inside, right? This is just at the top of the pole. This is just a switch. It doesn't have any intelligence to it. At the base of the poles where the relay is mounted, that's where the intelligence lives. And so you'll get your PTs here where we'll be monitoring line voltage and also stealing a little bit of power to drive the relay. Also, you'll notice that this is three separate units, one for each phase. So this is why this is called a triple single. Some units you'll have a bus across here. Um, all right, so these three will all be joined together and you'll have one operating mechanism. This one, they're separate operating mechanisms. So for this unit here, we can actually trip individual phases and then close individual phases. Something like this wouldn't be great if you were feeding a factory with it. You'd obviously, if you're feeding a three-phase customer, it's not good to remove one phase of power. So if you're feeding a three-phase customer, it'd always be all three or none at all. But if something like this was at the boundary where you split up into a residential subdivision and all your phases went in different directions and didn't combine again, or into a rural area where your phases didn't have three-phase customers, it was all single-phase customers downline. By having a recloser in this configuration, you could cut your outages down to just the affected phase or phases and leave everybody else on. Whereas if you had a gang operated unit and it was all or nothing, you wouldn't have that flexibility. You will find both styles of unit installed out in the field. So a little more about relays. We're going to focus on just modern relays. We're not going to focus too much on the old electromechanicals. The electromechanicals, you will find them. They're still installed out in the field. Um, Digital relays have been around for almost 30 years now. So you really only find the electromechanicals in some really old stuff or in some hydraulic reclosers, which are a beast unto themselves. I'll touch more on those next week. So if we take a look at the relay itself, these could live in a control cabinet with either a breaker or a recloser. These guys typically operate on 120 volt base, so whatever your primary is, doesn't matter. You can buy the same relay because you're going to use some instrument transformers and you're going to make it into 120 volts. And the instrument transformers will typically plug in back here along the top. And then you've got some communication ports. This particular one, that's a fiber port. You got Ethernet, you got serial, that's serial 485 usually. You'll have your CTs and your PTs coming in, and then these guys here are available for extra I/O points for different things you might want to monitor or measure or control. Now, one of the nice things about this is it's computerized, so you can make it program it to do pretty much anything you can imagine. And that's a really powerful thing. So, uh, the I mean, you consider compared to a fuse, what do we have on offer here? We've got indicator lights. We look at it and we know whether it's open or closed. On a current limiting fuse, we have no indication. On an expulsion fuse, we know if the fuse hanger's, hanging open, it's open. But on a current limiting fuse, we don't have any indication. With a breaker or recloser and a relay, we look at the relay and we immediately know if it's opened or closed. And if it was opened by hand or whether it tripped open on fault detection, it'll tell you right on the display panel. We've got a display panel. Some other advantages, we've got buttons. All right, so if you want to open this up, compared to a fuse, you got to get out the hook stick and you're going to give that a yank either from the bucket or from the ground. With a recloser or a breaker, if you've got a relay available to you, there's an open button on the front. Well, there's a trip button on the front, which means open. So you hit the trip button and it opens. You hit the close button and it's closed. And we've got communication ports, which means that we can plug these into a remote control system. Those are typically called SCADA systems in the utility industry. So SCADA, supervisory control, oops, and data acquisition. So these are systems that get used in utility control rooms, and they allow a remote operator to both see the currents and voltages at that point in real time, but they also allow the operator to open and close these units from the control room so that the control room operator has the ability not just to see, but to influence power flows through the network, which has some pretty significant implications for field staff like yourselves. So the big difference, and the really big difference that we're dealing with here, is that unlike a fuse, this can trip more than once. And that really does change the game when we're talking about temporary faults. So about 70 to 80% of the time, when we have a fault, the cause of that fault is temporary in nature. You know, consider a tree branch, right? Something the size of a cane or a walking stick. It falls on the line, it creates a fault, kabloom, it flies away. That tree branch can't hurt our distribution system, right? You think about a squirrel scrambling up a transformer and it goes phase to ground because it's stretched a little too far across the bushing and poof, no more squirrel. That squirrel can't hurt our distribution system. It could chew on our wires as long as it wanted. It couldn't hurt our distribution system. But what it can do is it can create an arc. And we already discussed how damaging those arcs can be. So what you end up with is if you're in an overhead distribution line, really high percentage of the time, when you get a fault on the system, it's not the thing that caused the fault that's the problem, it's the fact that you've drawn an arc. And as soon as you draw that arc, you got to get the power off to keep the arc from destroying your system. So what we want to do is we want to turn the power off, but we know that if we try turning it back on again, you know, 4 times out of 5, it probably stays back on. So this is the idea of a recloser. It recloses. And this is the thing that we can do when we have a relay attached to a recloser or a breaker that we can't do when we just have fusing. So this is great, right? So now we put one of these up and we have a fault and we turn the power off and then we can give it, you know, a couple of seconds to wait for things to settle down and we can close it again and we can probe that fault and we can say, hey, I'm going to try a second time. Is the fault gone? Yes? Awesome. Problem resolved. We try a second time. Is the fault there? Oh, crap. Still faulted. Open up. Maybe we'll try a third try. Last try. Try a third time. Power's back on and it holds. Okay, we're done. Third try. Power's back on and it's off. Whatever this is, it's not one of these. It's a permanent problem. Something's busted. Turn the power off, leave it off, and we're done. You guys have experienced this for sure, right? If you can think of, you get a big thunderstorm and you get a flash of lightning and then poof, the power goes out. And a couple seconds later, the power comes right back on again. And if you live out in the country, you might get a couple of blinks, and you know, depending where you live, it might be just one blink, or it could be as many as 4. But you know, if the power blinks and it comes back on and it goes out a certain number of times on that last one, if it goes out, it's staying out. Right? In Chatham, you just get one blink and then it's either in or it's out. Where I live, I get 3 blinks. If it stays out the 4th time, I know I'm done. And what that is it's those reclosers having detected a fault, and then they're going to open the circuit intentionally to let that fault extinguish, and then they're going to close back in again to probe to see, was this temporary? Is it tree branches or squirrels or strong wind? Or somebody threw some foreign interference as code for somebody threw some crap up into our lines. And so we're going to probe at that and we're going to say, is it temporary? Is it temporary? And You know, a lot of times the answer is yes, and then it stops and all is good. But if it's not, eventually you got to stop probing and just lock it out and be done. So the challenge to this is that reclosers and breakers are really expensive compared to fuses. So you can't just put them at every lateral. The other big challenge that we face is that our main three-phase bus, we tend as utilities to take really good care of it. You don't end up with trees growing up into your three-phase overhead on your main bus. Um, you know, they're well back from the roadway. They're or if it's a really exposed area, you'll put up a bollard, which is those concrete metal posts that sometimes protect stuff in parking lots or along roadways where people are worried about someone smacking into it. Um, but the faults are going to be not occurring on those three-phase buses so much because that's going to be really well protected. The faults are going to be occurring on those single-phase laterals going into subdivisions and down cul-de-sacs and down little side roads because those are the areas where the trees are. The residential subdivision is where the trees tend to be. So that's where you're going to get your fault. You're going to get your fault if you draw if you draw the diagram, right? Your recloser's located here, but your faults tend to be here on the wrong side of this fuse. And so the challenge that we try to face is how do we capture as many of these temporary faults so that we can keep all our customers on and we can avoid truck rolls because there's nothing there to fix. How do we keep that going if we have to keep our fuses coordinating so that if it is a permanent fault, if it isn't this, we still make sure that we're only putting the smallest number of people possible out of power. And the magic here lies in the fact that these relays, we can program them with a couple different behaviors. It's a computer. We can program it to do anything we want. And so what we do is we define two separate behaviors. We define an A curve and we define a B curve. And these don't have to be the same shape, right? So if these could emulate, for example, two separate fuses or have two separate shapes to them or pickup conditions, allowing us to change the reach of our protection. So if we take a look at this under normal circumstances, right, each transformer would have its protection zone on its secondary, and our fuse would have its protection zone here. And our recloser should have its protection zone here. And that is absolutely true for the B curve. That's our F1. But what we can do with reclosers, because of their advanced programming, is we can set up our A curve so that it stretches all the way past here. And we can set it up so that it actually goes faster than F1. And we can program that A curve to try and save F1. So what we can do is we can program that A curve so that it trips first. It goes before F1. It saves the F1. It changes F1 if the fault is here. It can allow F1 for the A curve. A protects F1. F1 is protected. And we probe, is the fault temporary? And when we're done probing, we revert back to traditional segmentation rules, right? No overlap in your zones, in your reach. And that would allow F1 to operate so that we didn't take the whole feeder out. We only took the downstream segment. So in that case, F1 would be protecting the B curve, but F1 is protected by the A curve. So this is what the diagram looks like in terms of space. Let's see what that looks like in terms of TCC curves. So what we're going to do is we're going to set up this to be our A curve here. So, and this is F1, and this is B. So we take a look at this in our sequence. And how we know the sequence of operation is included right here. If we take a look at this, the name of the recloser, it tells you its behavior. So in this case, we're going to probe twice using A. And then we're going to try 2 times using B curve. And we're going to lock out on our second B trip. Or we're going to open up and we're just going to stop trying after our second trip of the B curve. So we take a look. We have a fault. What we do is we see our fault comes up. We hit our A curve. A curve operates. Power goes out. Timer expires. Recloser closes back in. Breaker closes back in. Now we're on A number 2. Fault still there. We trip a second time. Timer expires. Now we're done probing. Now what we're trying to do is determine, is the fault located here where we would want F1 to operate, or is the fault located here where we need R1 to lock out and open and isolate this fault to keep it interrupted. So we probed with A twice. We know it's not temporary. If it was temporary, it would have been resolved. Now the question is the fault here and we want F1 to deal with it, or is the fault here? Going on the assumption that the fault is here, so we go A curve, then our recloser switches to B curve. Now the fault comes up and F1 is the device to operate. It clears the fault. This section of line here goes out of power. R1 stays closed and we're resolved, right? So that looked very much like traditional fuse to fuse coordination. Another scenario could be the fault is over here, in which case F1 would never see the fault current. If the fault was here, we'd see A curve, fault. A curve number 2, still faulted, open. B curve number 1, still faulted, open. B curve number 2, still faulted, open. That's the end of our sequence. Stay open, give up. Time to send somebody because whatever it is, we just put 4 hits into it and it's still wrong. So if we take a look at this graph here, there's a few more things I'd like to call your attention to. So one, we have to keep an eye on our coordination line, right? So F1 doing 140K fuse for it, and we have to consider the coordination line where that interacts. So we'd see that our coordination breaks down just around 5,000 amps for these fuses. So our A curve good to about 5,000 amps. After that, we're on the wrong side of our coordination margin line with our 140K fuse. Now in this case, I've got our recloser pretending to be K-speed fuses. We don't have to do that. We can make our recloser pretend to do anything we want. So now you'll also notice that up here, our B curve, which is emulating a 200K, it doesn't have a coordination line. So there's no coordination line because you don't need to allow coordination margin on a recloser. So reclosers don't need coordination margin. And that makes sense when you think about it because it's a computer. It's going to behave exactly the same. Computers don't care if they're hot or cold. Computers don't care if you run them near their limits or way below their limits. That doesn't bother them at all. There's nothing here that's getting hot, right? There's no preloading effect. We've got instrument transformers. They're designed for that. They really don't care if they're run at their operating ratings or not. Their output is going to be exactly the same. So all those factors that cause us to need a coordination margin when we're doing a fuse to a fuse don't really apply when we've got a recloser or a relay driven device, recloser, breaker, anything with a relay. It's the relay that doesn't really need that coordination margin. They're going to be very consistent. Another thing I wanted to call out here is that the names change. It doesn't make sense for you to say that the recloser has a minimum melt because nothing's melting. We hope. If things are melting, things really went wrong. So instead, we have new names for things. This curve is called the pickup. This is the point where the recloser has decided that it is going to act. So at this point, the electrical decision is made. I am going to open, and it sends the command to the switch or to the breaker and says, open. We still have a clear or a max clear. And this is the time by which you're guaranteed that the breaker or switch has opened and snuffed the arc, breaking the conduct. There's no more electricity flowing. Circuit is open. And that always takes a little bit of time because the breakers have to physically swing that switch arm open, and then they're going to draw an arc internally and they're going to deal with that arc internally. So that always takes a tiny bit of time for that to clear. And so there's a gap between when we pick up and when we finish opening. So let's do an example. Let's develop a fuse saving protection settings for a line recloser. And we want it to coordinate to a minimum of 2,000 amps with an 80K fuse. So here's our 80K fuse. It's protecting a lateral line, and we want to develop some settings that will allow us to coordinate with it. So we got a fuse here. So the very first thing we need to do is start understanding what our coordination margin is. Let's take a look at that. 1, 2, 3. Call that 3,800. Let's call that 1,200. 1150 there. And let's take a look at this guy here. 1, 2, 3. That's really close to 400 right on the nose. And we can keep building out our table until we're satisfied. Now we're going to apply our derating factor. We don't have any special information, so we're going to use our 75% rule that we covered in our fuse-to-fuse coordination lecture. I'm typing that into the calculator. Gets us so we can now start plotting these points. And 2850, and we can do 862, and we're going to do 300, and we could keep going up, and then we're going to draw our line. And we're going to take this line we developed and we're going to plot it on a family of fuses. So this is our coordination line. And we were told we had to coordinate out to 2000 amps. That was given to us in the question. So the question then becomes, if this is 2000 amps, here we're looking for the biggest fuse that crosses this coordinating line on this side. So crosses at some value larger. So this fuse here would be too short, small. This fuse here is pretty marginal. This fuse here is definitely good to go. So we can follow these lines up. And if we follow this line all the way up, we should end up at 25K. So we have a look at those two in the clear, and we can see that our coordination line and our 25K maximum clear meet somewhere around 21 or 2200 amps. Greater than the 2000, so everything is good. If we were crossing over here, that would indicate that we were not properly coordinated to the 2000 amp marker, and that would be bad. So we've got our 25K, which represents our A curve. So when our recloser is acting as an A curve, it's going to be operating before our lateral line fuse, protecting it and allowing us to probe and address our temporary faults. So now we can go back in here and we can pick a fuse that's going to coordinate on the high side out to 2000 amps with our 80K fuse. And that would be pretty much everything bigger than 80K because our 2000 amp line is here and nothing crosses our 80K max clear that's bigger than 80K. under that value. So we don't, right? So any 100, 140, 200 are all acceptable answers. We're going to grab the 140. And so what we're left with here is we get our A curve, our fuse, and our B curve. And we've got our margin. We can see that we're coordinated to some number greater than 2000 amps down here. So this is the answer that we're looking for if the thing is select a set of curves for the relay that coordinates with an 80K fuse. Now there is one comment I'd like to add to this one when we're talking about our major assignment. And that is, you saw that our fuse got an awful lot smaller. Our A curve is really, really fast compared to our expulsion fuse at the lateral tap. It's very likely that 25K, if we were in this situation, 25K might be too small to coordinate with this transformer right here. It also might be too small to coordinate with this transformer here. So what that would mean is that the first thing you would solve isn't F1 when you're trying to solve this. It would be, what's the requirement for my A curve? And then I'd pick my F1 so that it coordinated with my A curve for fuse saving. And then after those two things were done, then I'd go and select my B curve. Hope you guys have found this enlightening. Looking forward to continuing our course together. Have a good week.